Alright, first part of this lesson of linear to quadratic systems asks us to count the number of points of intersection between the two graphs after drawing a rough sketch of a parabola and a line on a coordinate plane. So I just draw my x and y axes, and it's just a rough sketch. They just want nothing exact. But let's see. Here's my parabola, and let me draw just a line across this way. Alright, it says count the number of points of intersection between the two graphs. I've got a point of intersection here, and I have a point of intersection here. So total, I have 2 points of intersection. Part B says sketch another parabola on a coordinate plane. Alright, and they tell me to use a straight edge, but I want you to be able to see it a little better than that. So I'm going to show you the different ways that a line and a parabola could intersect. So above you saw where they could intersect using 2 points of intersection. We could cross right here at the vertex and only have 1 point of intersection. Or I could cross down here, just cross the y-axis, and never have any points of intersection. So how many different numbers of intersection points are possible between a quadratic function and a linear function? So we could have, or they could have, 0 points of intersection. We could have 1 point of intersection. Or we could possibly even have 2 points of intersection. Alright, so now they want us to try to determine the number of solutions. This is where that Desmos is going to come in very handy for you guys. I know we used it some last chapter, so we're going to kind of look at it more today. And we've got y is equal to 3x squared, and y is equal to 3x minus 2. Let's take a look at this. Determine the number of real solutions this has. Doesn't matter how far I zoom out. It doesn't look like this graph is ever going to touch, does it? So the number of real solutions that this graph has would be no real solutions. Well, why would it be no real solutions? The reason it would be no real solutions is because it never ever touches. The two graphs never touch. If you want to kind of draw a sketch of this and what it looks like so that you can see, so that you can remember, these two graphs are never going to touch. Now for number 2, they want us to solve a system of, or a linear to quadratic system using substitution, but again, we're just going to use graphing because it's nice to have this little graphing tool right here. So I'm going to go ahead and type in both of these equations. So I've got y is equal to 2x squared minus 6x minus 8, and 2x minus y is equal to 16. Well, 2x minus y is equal to 16. This graph only crosses at one point. They only intersect at one point, and that one point is 2, negative 12. So if you want to, and it might not be a bad idea to just kind of show over here what the graph looked like. We had a point, one point here that it crossed at. All right, now my next equation. Negative 3x squared plus x plus 4. 4x minus y is equal to 2. And it looks like this graph crosses in 1, 2 places at the points negative 2, 10, or negative 2, negative 10, and 1, 2. And the graph of this looks something to this effect, where we had 2 points of intersection. All right, the next question says, revenue for the high school band concert is given by the function y is equal to negative 30x squared plus 250x, where x is the ticket price in dollars. The cost of the concert is given by the function y is equal to 490 minus 30x. At what ticket price will the band make enough revenue to cover their cost? So I went to Desmos again, and I put both equations in, and I found 2 points of intersection. Found a point of intersection at 233 and a point of intersection at 7. So we're looking at the ticket price in x. So we're looking at the x values. So at what point would the band make enough money? The band would make enough money if the ticket prices were between $2.33 and $7. They would cover their revenue that way. So on my paper, I'm going to write when ticket prices are between $2.33 and $7. Next one tells you, they don't give you a graph, but they tell you to use this or to solve it using shading, so we'll just kind of talk about it. It's the same as if you had a linear equation like we did last week. We had 2 linear equations, or maybe 2 weeks ago, I can't remember when. So anyway, we've got your quadratic equation, we've got our linear equation. And let me get back to the home. So do you see this where they overlap? This would be our solution region. So our solution region, if we were just looking at the x values, would be from negative 6.217 and 3.217. So all I was doing here was looking for that common shaded region. They didn't even give us a graph to shade. So more than likely, if you were to see something like this, you would have to choose a point in the area. And then this part right here, we're not going to worry about. Alright, so we're also going to take a look at the parts of a radical. Alright, I'm not really worried about the different parts of a radical more as I am you solving a radical. I know some of you have had issues with that in the past few lessons, so I just thought today would be a good idea to go over that with you guys. So, first 12 perfect squares. We got 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10, 11 times 11, and 12 times 12. These are our first 12 perfect squares. So, it says the first 9 are perfect square roots, so let's take a look at this. The square root of 81. Everybody should know the square root of 81 is equal to plus or minus 9. Square root of 484 is equal to plus or minus 22. Square root of 64 is plus or minus 8. 18 times the square root of 4, so that means that it is 18 times plus or minus 2. So 18 times 2 is 36, so that would be plus or minus 36. Square root of 256 is 16, and 3 times, or plus or minus 16, and 3 times 16 is plus or minus 48. Kind of getting the hang of this here, right? So negative 5, or this would be the square root of 11. So this would be plus or minus 11, plus or minus the square, or 55. These are much easier than they seem. You break it down, square root of 1 divided by the square root of 16, which is 1 over 4, or plus or minus 1 over 4. Same for this one, square root of 9, so plus or minus 3 over 10. And then this one would be plus or minus 5 over 7. Not bad, you just break it up as 2 separate ones. Now they want us to simplify non-perfect square roots. I'm going to work the even problems with you and then let you to work the odd problems by yourself. Square root of 24. So remember that calculator trick I told you. 24 divided by x. And we're going to look for the largest perfect square. Well, the largest perfect square I see is the number 4. And 4 times 6 gives me 24. So I'm going to write this as the square root of 4 times the square root of 6. Well, what did we just say the square root of 4 was? That's plus or minus 2. So my answer would be plus or minus 2 times the square root of 6. All right, the square root of 72, we're going to do the same. I'm looking for the largest perfect square, and it looks to be right here at 36. So I've got the square root of 36 times the square root of 2. The square root of 36 is 6 times the square root of 2. The square root of 90. Alright, looks like it's going to be the square root of 9 times the square root of 10, or plus or minus 3 times the square root of 10. $162. Starting to get a little bigger on us. 162 divided by x. We look for that largest perfect square, and that largest perfect square is actually here at 81. So the square root of 81 times the square root of 2, or plus or minus 9 times the square root of 2. 343. It's going to be the square root of 49 times the square root of 7, plus or minus 7 times the square root of 7. And then the last one I'm going to work with you guys is 28, and I know that's the square root of 4 times the square root of 7, or plus or minus 2 times the square root of 7.